Hello students, this is Mr. Allen, and today we are going to look at section 8.3, which is on the integral test and P-series. The objectives here are for you to be able to use the integral test to determine whether an infinite series converges or diverges, and also to be able to use the properties of P-series and the harmonic series, which I'll talk briefly about today. In general, it's difficult to find the exact sum of a series. So what we're going to do in most cases is, instead of actually determining the sum, which we can on some things like the geometric series, is we're just going to determine whether a series converges or diverges and not be so concerned with the exact value. We were able to compute, like I said, the geometric series. But usually there's not a formula that we can actually find the exact answer. In fact, there's many cases in mathematics where they still don't know the answer to some very common series. So let's look at this series here. So this is an infinite series, and the formula for it is 1 over n squared. We're going to start with n equaling 1 and going through infinity. So some of the first terms would look like this. So let's go ahead and estimate some of the partial sums of that series. So in the table below, we can see that when n is equal to 5, the sum is 1.4736. And, as we go all the way up to 5,000 terms, we can see that the sum is only increased to 1.6447 approximately. So even though this sum is increasing, this series, the sum of the series is increasing, we can see that it seems to be slowing down at a rate, and it's going to approach some value. So in this case, we can see that it's approaching about 1.64 as n goes to infinity. So it looks like this series is going to converge. So we can confirm this expression with the geometric argument. So let's say that we graph the function y equals 1 over x squared. That's the blue curve here on the graph. We can inscribe rectangles underneath that curve above the x-axis. We can see that that first rectangle would have a height of 1 and a width of 1, so the area is basically 1. The next rectangle would have a width of 1 and it would have a height of 1/4. The next rectangle would have a width of 1 and a height of 1/9. So the base of each rectangle is 1. The height is equivalent to the function y equals 1 over x squared at the right endpoint. So the sum of these areas of the rectangles is the infinite sum of 1 over n squared. So we're just talking about those particular rectangles. And again, I'd like to note that all of those rectangles are underneath the curve 1 over x squared. If we exclude the first rectangle, which is that 1 by 1, the total area of the remaining rectangles has to be under the curve 1 over x squared when x is greater than or equal to 1. But what we can do is we can actually evaluate the integral, or the exact area under the curve, not just the area of the rectangles, but all of the area under the curve, using the integral 1 to infinity 1 over x squared dx. This improper integral is convergent and it has a value of 1. So back when we looked at chapter 7, at the end of chapter 7, at the end of last semester, we would have been able to evaluate this. And we find that indeed that has the value of 1. So the claim is that the sum has to be less than or equal to 1 if you think about it that way. Okay, so the curve has an area, once you get past 1, of exactly 1. That first rectangle had an area of exactly 1. So that means that the infinite sum of 1 over n squared from 1 to infinity has to be less than 2. Thus, this series converges. Now notice I'm not telling you what the sum of those infinite number of fractions is. I'm just telling you that we know that it converges. And it's roughly about 1.64 that we mentioned earlier. Let's look at now at a different series. So this one is the infinite series 1 over the square root of n. So let's look at some of the partial sums of this series. So when n is equal to 5, the sum is 3.2317, and it grows just like the last one did. But now look what happens when we're at 5,000. So now this thing has grown to 139.9681. So hopefully you get a sense that this one's growing in a different way. The other one was growing, but it was growing at a slower and slower rate. This one is not. This one is growing at a faster and faster rate. So this would make us seem to think that it probably is divergent. And it turns out that it is. And we can use the same argument. This time, though, what I'm going to do is I'm going to use circumscribed rectangles. And what I mean by that is now the rectangles are going to be drawn up above the curve. So these are left Riemann sum rectangles, if you will. And if we just look at the area from 1 to infinity, we can use this similar approach of the area under this curve using integration. So if we look at the base of each rectangle is still 1. The height of this is the height of each rectangle is the value of 1 over x square root of x. Here we're using left endpoint. Okay, so I said all that. So the sum of the areas of the rectangles is as follows. This total area is greater. So we've got the rectangles are now, they're above, each rectangle was above the curve. But we know that this improper integral is divergent. So the integral from 1 to infinity of 1 over the square root of x is divergent. In other words, it's an infinite. In other words, the area under the curve is infinite. So the sum of the series also has to be infinite. We know that the area under the curve is infinity. But notice that each of our rectangles for this series is above the rectangle. So it's got to be greater than infinity. So it has to be divergent. And again, this one's even easier. If it's greater than infinity, then it's got to be a divergent, and we can't associate a number with it. Okay, so now we're going to get to this is the most important slide. I guess there's two. This is one of the two most important slides. This same sort of geometric reasoning can be used for these two series, can be proved using the following test. Now, before I show you the theorem, the test that I want to do today, I want to remind you of P arrow Q. So this is an if-then statement. We go all the way back to geometry and we talk about logic. If P, then Q. So in order to conclude Q, P must be true. Okay, so these are if-then statements, and here is the integral test. Very important slide right here. Suppose that f is continuous, positive decreasing function, and we have this series that's going to go from n equals 1 to infinity. For that to be convergent, here's what we need to know. If the integral from 1 to infinity of f of x, which is basically the function that is equivalent to the expression a sub n, if that integral is convergent, then the series is convergent. So that goes back to that first example we looked at. When we had all the inscribed rectangles, we found that the area under that curve was 1, right? So that was a convergent integral, if you will. Therefore, the series has to be convergent because the series was all the little rectangles underneath it. 2, if the integral from 1 to infinity of f of x dx is divergent, this is like the second example we just looked at, then the series has to be divergent. So this is the integral test. This is something that's very important that you need to know. So test the series. The infinite series, 1 over n squared plus 1, we're going to determine if it's convergent or divergent. So the function that we're going to look at here or use here is instead of using 1 over n squared plus 1, we're going to use f of x equals 1 over x squared plus 1, which is the same function, but just in terms of x, and we're going to write it as a function. It is continuous, it is positive, and it is decreasing. Now, decreasing means is that we go further down the line, the value of y is smaller. So we can go ahead and apply the integral test here. So let's see what happens. So we'll do the indefinite integral from 1 to infinity of our f of x, and that is going to be what we call an improper integral. So we have to do the limit as t goes to infinity. We've done this in the past. This is the last part of chapter 7. So the Antiderivative of 1 over x squared plus 1 is the arctan. We need to evaluate that arctan from 1 to t, where t goes to infinity. And so we're going to go ahead and do that by substituting in. And by the way, the tan of 1 is pi over 4. So, and the the arctan of infinity is pi over 2. So it's pi over 2 minus pi over 4, which is pi over 4. Now here's the important conclusion to make. Thus, the improper integral 1 to infinity is convergent. Therefore, by the integral test, the infinite series is convergent. The sum of the infinite series is not pi over 4. The only thing we're using this integral to do is to determine if this series is convergent or divergent. So the answer is it is convergent by the integral test. Here is the second most important slide. So this is another one you want to definitely make sure you know, and this is for P series. This one's actually even easier than the last one, because the last one you basically have to evaluate an improper integral, which can be difficult. So here's what you need to know about a P series. A P series is any series, infinite series, from 1 to infinity, where it's 1 over n to the P. Okay? This P series is convergent if P is greater than 1 and divergent if P is less than or equal to 1. Now, please note the following. The n here is the index that's changing throughout the problem. And I'll show you an example of that in a minute. P is a constant. P is a constant, n is variable. So let's look at an example of this. So here we have an infinite series. This is a P series because it has the form of 1 over n to the P. In this case, n is still n, but P is 3. So when we look at our rule here for P series, n is 3. I'm sorry, P is 3, and if P is greater than 1, which it is, this series has to be convergent. That's all you have to say. Once you recognize that a series is a P series, you can simply use this P series test and you're good to go. You don't have to do anything else. All right, so let's look at another example. Consider the following infinite series, 1 over n to the 1/3. This is the same thing as 1 over the 3rd root of n. So here are some of those terms. Here we have a P series, but in this case, P is 1/3. P equaling 1/3 is less than 1. Therefore, this series has to diverge. In other words, it's going to grow without bounds. By the way, both of these examples are very similar to the first two that I did to illustrate the integral test. So basically, the P series follows from the integral test. All right, so now I'm going to mention something called the harmonic series. This is the most compact way I can write the harmonic series. It is an infinite series from 1 to infinity of 1 over n. Here are some of the terms, 1, 1/2, 1/3. And I'm mentioning this series, and I'm not actually going to do an example of this. First of all, I hope you recognize that this is a P series. And then I could ask you the question, does it converge or diverge? And based on the last important slide that we talked about, hopefully you can answer that very quickly. But if not, you might want to look back and figure that out. So I'm mentioning this because this is probably, I don't want to say it's the most important, but it is one of the most important series that we look at in mathematics. It has a lot of ramifications and it comes up in lots of problems. You may want to look it up on YouTube, or here I've got a little snip from Wikipedia. There's a lot of information about it. You really need to be familiar with this harmonic series. So this is essentially a P series with P value equaling 1. All right, so let's look at another example here, and this one's a little bit different. This is not a P series. This says determine whether the series ln of n divided by n converges or diverges. So the function we're going to use here is obviously going to be the ln of x over x. This function is positive. and it is continuous for all x greater than 1. And it is continuous. But it is not obvious whether or not f is decreasing. So we must compute the derivative. Remember, one of the things that when you do the first derivative does is it tells us if a function is increasing or decreasing. So we will use the quotient rule here, and we get the following derivative. And with a little bit of work here, we can see that we're going to end up, after simplification, 1 minus the ln of x over x squared. Now, clearly, the bottom here is positive because we're talking about 1 greater than or equal to 1. Is the numerator greater than or equal to 1? Well, we've got 1 minus the ln of x. So what is the value of ln of x once you get past 1? I apologize here, but my screen's not going forward. There we go. So it turns out that the ln of x is greater than 1 once you get past 1. So that means that f prime is greater than 1. Is less than 0 because the ln of x is greater than 1. That is, x is equal greater than e. It follows that f is decreasing. So we do know that it is indeed positive. We know that it's decreasing and all of those good things. So we can actually go ahead and use the integral test now, which is what we're going to try to do. So we're going to integrate from 1 to infinity of the ln of x over x. That is an improper integral. So the antiderivative turns out to be the ln of x quantity squared divided by 2. We need to evaluate that from 1 to t. That gives us the following. And with a little bit of work, we see that that is infinity. So this turns out to show us that the conclusion we can come to is that this improper integral is divergent, and therefore this series also has to be divergent by the integral test. Notice I did not use the p-series test because this is not a p-series. And that will be that. Thank you guys very much for your attention.